Now we want to go into the design principles of the FRA design, of the frequency response approach design. And I want to execute all these steps with a special example. Example helps to understand principles. This example you can find on the pages workbook 36 and following pages. And the process, together with actuator and sensor, behaves like a series of 4 PT1s. So it is not necessary to know the transfer function. Here the transfer function is given. Note that it's only necessary working with a Bode plot, which you can measure. Now you need just a measurement device for Bode plots, such as gain phase analyzers or other devices who can do this job for you. In our case, we have given the transfer function, so we can execute all things also with other principles of design, and we can of course put these blocks into my simulation program, which needs blocks, which needs transfer functions, and then we can try to simulate these systems. Note that it is impossible to calculate, for example, Laplace transformation results with the system, because we have here a 4 PTI, fourth order system. If we add a controller, if it is only a P controller without any P, then without any complex frequency P, then of course we have a fourth order system. If we close the box, it's also a fourth order system. And in my Laplace table, we have no equations, no rows for systems which are higher than 3. So mathematically we cannot do anything. So Bode plot works. In Bode plot design, this could be a series of thousands of PT1s and any combinations of PT1s and PDs and PDT1s and so on. So it doesn't matter. The structure of the system must only be one input, one output system. We have to measure between this point and this point the open loop Bode plot. Okay, what I want to do is the following. I want to fill this table, and you see here I want to play with now different types of controllers. In project 1, cruise control, we have worked with just a simple PI controller, and we have used pole compensation. In our project 2, we have worked with a PIDT1 with pole compensation. Here I want to show you an alternative to pole compensation, and I want to show you what happens if I use not a PI, a PIDT1, if I use a PDT1 without I, a pure integrator, or just a pure P controller. So here you learn the comparison between different types of controllers. You see here this column contains omega d, which is the speed index. The higher this value, the faster the loop. Here these are parameters, design parameters, which coming out of my FRA design. This is a value I will explain later. That is the time constant of a differentiator part. So here in the first 4 rows there is no TV. Same with step depths. Step depth is only valid here for the last 3 rows. And here I make some remarks. And this should be the reference disturbance error I want to list up. Okay, now look for this system, which has just a gain of 2. This is gain 1, gain 1, gain 1, gain 1, gain of 2. Note that the sensor here is just replaced by a P block with a gain 1, so we can of course remove this P block, because this has no effect. In the last example I will show you here in the bottom page, then there will be a sensor with a gain. So I think note that in this situation the sensor is neglectable, and any dynamical behavior of a sensor is just covered with one of these blocks here in the bottom. These numbers coming from a power system in power electronics, but it doesn't matter what this is. Let's assume that this is a speed control. This is the speed of a system, and we want to control the speed by giving the desired value for the speed. And the power system here has 4 PT1s with 4 different time constants. Here you see 330 milliseconds, 50 milliseconds, 1 second, 10 milliseconds are the values. And we have to first draw the Bode plot of the process. Please note that the controller is at this time undefined. We start with the Bode plot of the process, which we assume to be given or measured. That's the basic fact of FRA design. In workbook, you can find on the page 38 the Bode plot of this 4 PT1 system. This Bode plot is given with 2 curves, a blue curve and a red curve, and with 2 scales. On the left side there is a magnitude scaling in dB values. On the right side is a phase curve scaling. You have to know that the red curve is a phase curve and the blue curve here is the magnitude curve. And on the horizontal axis you can see this is the logarithmic value of the omega radian frequency. You see this logarithmic axis, but the numbers here are not the logarithmic values of omega, but the omega values. So here we have omega 0.1, 1, 10, 100, 1000. So you see this is a decade. We have a 1, 2, 3, 4 decades Bode plot. Here we have big lines between 20 dB. Here big lines also defines 40 degree phase value. I can make this curve larger with my fingers. I have a touch screen, so I can show you some more details. You see there are some lines here. These lines will be explained now in the next step. This is a series of PT1s. Note that the PT1s are just described in chapter 3. The Bode plot of a PT1 starts with a horizontal part for low frequencies and for a minus 20 dB over a decade, a drop for high frequencies, and the phase goes from 0 to minus 90. If I have a series connection of these blocks, then there is a horizontal part for very low frequencies, and the K is then defined for the total K. In our case, the K is 2. That means 6 dB. And the phase is summed up for all 4 PT1. So finally, we have a phase shift. 4 times minus 90 is minus 360. Let's look if we can see this in our diagram. First, I go back to the DC gain. You see the DC gain here is 2, which is 6 dB. This is all ones. 1 is in dB value 0 dB. If I add them, they have no contribution to the total gain. 2 is the DC gain for the total system. Note this, and now we look into the diagram on page 38. First, the DC value here you see is a constant line. Here the drop starts, the decrease starts, and here you see the line here at 10 dB, 0 dB gives that this line exactly is plus 6 dB. And then this will become steeper and steeper, and finally, if we make this long enough, this decrease will be 4 times minus 20 dB over decade. So this becomes minus 80 dB over indicate gradient asymptotical curve. The same with the phase. The phase diagram starts here with 0 degrees in the top. You see the phase is all negative. If you see here a grading of minus 40, 60, 80, 100 down to minus 200, and here the curve ends. And I have deleted all other parts of the curve because normally we have phase wrapping at minus 180, and then this curve is continued with a shift of plus 360 degrees because the sinusoidal signal has no change. If I shift the signal of completely one period, and one period is in phase shifting 360 degrees. But I have wiped this out because our interest is only in the region before I reach minus 180. Yeah, so that's some information for the Bode plot. We assume that this is given, and in examination, for example, then a Bode plot is given, and then you have to work with the given Bode plot. Yeah. Okay. Some notes in my writing. Chapter 5.2, FRA Design with my 4PT1 example. Bode plot, you can see I have shown it, see workbook page 38. And what I want to do is I start with the most simple controller, the P controller. Here you can learn many things of the idea behind this FRA design, because a P controller is very simple, has just one degree of freedom. Here is the control difference at the input, this is the controller output. A P controller has just a very simple transfer function, which is K. Let's call this KC. And KC is free choice. The question is, no, of course, now I can select any K and look what happens with the loop. But the thinking in controller design is now in the other direction. The main principle of FRA design is I look for my indicators, stability indicator and so on, and speed indicator and accuracy indicator, and I select one of these indicators and go back to ask then what is the controller parameter. Yeah, the idea is I want to design the user parameters and then want to calculate the relevant K's and T's of my controller. If I have only 1 degree of freedom, I want to select the most important of these parameters, and the most important is stability and damping. Yeah, sometimes you can accept slow working or inaccuracy. This is not so I think important, as if I have only one knob which I can change. Most important is that it's just coming out of practice is the damping. So what I do now in this situation, I design phase margin. I select a phase margin, positive value, and I want to start with a default value, which is phase margin 60 degrees. This gives mostly an acceptable overshoot, and note that if I advance after designing and checking and I see that the overshoot is too large, I can decrease just simply the KC value of the controller, and then I can decrease overshoots. So this could be a good starting point. And in many cases, yeah, we stay with this value. 60 degree is the standard default value of phase margin in FRA Design. And I want to check now what happens if I select this. Of course, I want finally to have a KC. I want to have an omega d value for the speed and DC gain for the accuracy and so on. So if I have selected this, I want to find out all the other indicators, and then after this, of course, I want to simulate this system and check if my predictors here are showing in the right direction. Okay, what can I do with the given phase margin? With the Nyquist equations, I can do my job. Note that the Nyquist equations are here. I should mark this, or just with yellow. The Nyquist equations are very important. So I work with the Nyquist equations, yellow marked here in my paper, because here the phase margin is given. So I can now check what happens with this equation. I can now calculate the open loop phase of my system. Is then also given, calculatable. Yeah? So with Nyquist, I can say, okay, open loop phase at omega d is phase margin minus 180. And in our case, this is 60 degree minus 180. And this is simply calculated to minus 120 degree. So this is the equation which define the crossover frequency value, because the phase curve is given. No, stop, wait for this. With this I can find out the crossover frequency. Yeah, I select phase margin and find out the crossover frequency if this phase curve is given. Open loop phase. Open loop phase is the sum of the controller phase plus the process phase. Process means with actuators and sensors. Yeah, note, phase of PAS is called phase of process, including actuator and sensor. If you measure your Bode plot, of course, then you have the input of the actuator and the output of the sensor, and you can only measure this phase curve with your Bode plot measurement device, with your gain phase analyzer. So this curve contains all parts except the controller. In our case, we know P controller has no phase. So in our chapter 5.2.1, we can say, okay, in this situation, my open loop phase is identical to my measured process actuator sensor phase, and I have to find the point minus 120. This delivers my omega d value. Let's look into my diagram of my workbook, page 38. This is marked here with my red dotted lines. At minus 120, now I find the cross point with this phase curve. Phase curve is red, and the cross point exactly defines my crossover frequency. So at once, if I select I select the phase margin, at once I can find out the crossover frequency. If this is 1, this is 2, this is 3, 4, so this is around about 2.7. If I exactly calculate this, I end up in 2.68. So the definition of my phase margin leads in exactly the result for my speed indicator, 2.7. Okay, with the speed indicator I can estimate my Tmax value of a reference step response is roundabout 4 divided by 2.7, which is roundabout, because this is rounded to maximum 2 significant digits, I can say this is 1.5 seconds. So if this is fast or not so fast, at this time we cannot say, but this is a good value to compare other controller designs, which can be faster or slower. Yeah? So this is an indicator for P controller. We don't know the hardware, so we cannot say if this is fast or not. So this is just a starting value. What can we do more? Now we have omega d. We know with Nyquist, that is Nyquist, the second equation. Now I go to Nyquist first equation, red marked. Note that the open loop magnitude at omega d should be 1 or 0 dB. What is better for you? This equation leads to the following statement: open loop at omega d. Omega d is known, should be 1. This is the magnitude of the controller at omega d multiplied with the magnitude of the, I write down, process actuator sensor, that is coming from the diagram, at omega d. This must be 1. This may be a help to find out the Kc value, because in this equation the magnitude of my controller FFP is just Kc. That's the fundamental basics knowledge of a P controller, that the gain is independent of the frequency, always Kc. So this is our unknown value Kc. And what is this? We have to look into the curve from my Bode plot. From curve, so go back into the curve, and what I now see is, now I have to go to the blue magnitude curve, to this point. This is the gain of the process, actuator sensor, at my desired crossover frequency 2.7. So at the cross point of the phase at -120, I go now up to the magnitude curve and have to read now the value at my left axis. And you see in this case, this cross point ends up in a scaling. If this is 0, this is -10, this is -6. So from curve, I read -6 dB. -6 dB. What does that mean? I have now an equation. The result is 1. The product of this value and this value must be 1. This value is Kc, unknown, and this value is now 6 dB, which is in factor. If I multiply this, of course I need the factor, so this is equivalent to 0.5. So what we can calculate now is Kc. Kc is 1 divided by this is 1 divided by 0.5, and this is finally 2. So the given phase margin leads to a resulting omega d value 2.7, and this omega d value defines here in this equation the unknown Kc value. So with this Kc value now I can simulate it or build it or test it, doesn't matter. I have just now all information to check this closed loop system. We have a further indicator. Note my objectives and indicators. Stability is given with 60-degree phase margin. Also a well-damped system is given. We have now a speed indicator for this omega d, and now last Last indicator, we could check the accuracy indicator, the control difference in a reference step response. The control difference is 1 divided by 1 plus open loop gain at 0 frequency. Okay, accuracy, check accuracy. XD for large times is 1 divided by 1 plus open loop magnitude is again controller gain at 0 multiplied with the process actuator sensor gain coming from the Bode plot or from other information at 0. In our case, this is clear. This is Kc, and Kc is calculated to 2. How large is the open loop gain at 0? Look into the diagram. Here you have to go to small frequencies. If you have measured it, look, if this is a horizontal line, then we assume that we can approximate the 0 point. It's not here and not on another decade deeper, then we have 0.01 and so on. So the 0 value, the DC value, is not in this diagram. So we have to extrapolate this situation to negative infinity. But if this is a horizontal line, we assume that the DC gain is 2. This is different if we have an integrator. So look for the project number 4 in the end of this lecture. Then we have a process which has an integrator. Then we have here a gradient of minus 20 dB over decade. Okay, we know the signal block diagram of the system, and I have told you that the DC gain from block 2 down to block 6, the DC gain is 2. So yeah, this fits to our knowledge, but note that only the Bode plot is given. This is normally not known, but in our case we know the DC gain of the process is really 2. So we can say from curve, this is plus 6 dB, equivalent to factor of 2. So we have the following result: 1 divided by 1 plus 2 times 2. 2 times 2 is 1 divided by 5 is 0.2. That means if this is a reference step response after a unit step at the desired input, we want to have a 1. We get an error of 0.2. This is an error of 20%. We can say if you want to have a 1, we are 20% deeper. If you want to have 100 degrees centigrade, we get only 80. If you want to have 10 degrees centigrade, we get 8. So there is a constant, well-known error, but there is an error, a control error of exactly 20%. Okay, in the next video, this is video 50, in the next video I show you this system simulated with my program FRA C#.